Do you want to know what this rock is that I'm holding in my hand? I'm going to tell you. This is basalt. What's basalt? Basalt's a lava. Is that not mad that this is a lava? This comes out the ground at 1200 degrees Celsius. It's very hot, which means it's, you know, it's magma, right? Essentially, it's moving through the crust as magma and it erupts at the surface as lava. And then it crystallises very quickly, right? Forming a very fine-grained igneous rock. That's what lava is, that's what basalt is, okay? So we're going to go into the details about how this forms, and then we're going to go into the details of basically about different types of basalt and stuff that you can find in Scotland, okay? Well, it's all the same stuff, it's all the same composition. But to get a basic understanding of how basalt forms, we kind of need to go into igneous processes a wee bit, right? So I'm going to start drawing things and hopefully you guys can see it and understand. And I've got my wee dog in the background as well, Tala. Right, okay, so this is earth, you know. We've got earth's made up of layers, right? Like an onion, but no as many layers, okay? So we've got like our inner core, our outer core. I mean, this isn't to scale. Our mantle and our crust. Now there's two types of crust, okay? You've got oceanic crust, which forms at mid-oceanic ridges, and that's where we mainly get basaltic lava forming, right? Where two plates are moving away from each other. So this is a divergent plate boundary. Right? So those two plates are moving away from each other, and the crust is very thin when it's oceanic crust. And you also have continental crust, right, which is a lot thicker. Continental crust can be, you know, like 25 to 60 kilometres, like, thick or something like that, right? This is like 5 kilometres to, I don't know, 10, 15 kilometres thick. So it's very thin. Oceanic crust is very, very thin, right? So to get an understanding of how like basalt forms, we kind of need to understand these processes, right? So basically, when you have plate boundaries and you have plate tectonics and stuff like that happening on a planet, well, we're one of the only planets in the solar system that it actually happens in. You have this divergent plate boundary, and what basalt is, basalt's actually a partial melt of the mantle. So when you have this divergent plate boundary where the oceanic crust is being formed, Tala, sit down. Right, so this is the sea. You have what's known as mantle convection, right, that kind of like pushes this. And then it subducts elsewhere, okay, because oceanic crust is like a lot thinner, and it's denser and it will subduct under. So this is a mantle, you know. This is mantle convection going on. And what happens is you have a partial melt of this mantle, because the mantle is not actually a liquid, the mantle is a solid. We know this through seismic waves and stuff like that, right, in geology. But when I'm saying solid, it's not like rock solid, it's basically like a putty or a clay. It acts like a putty or a clay, like it moves very slowly over geological time, sometimes melting. So when this melts at mid-oceanic ridges, like the Atlantic Ocean today, and the Atlantic Ocean is split apart, and you've got the Eurasian plate going one way, and you've got like the North American plate going the other way. This is like forming basaltic lava or basaltic magma. Because when you partially melt this mantle, you take a little bit of the mantle away, you're then changing the composition of that mantle and it turns into basalt. So the mantle originally is known as peridotite, and sometimes we find peridotite like up, it shoots up, right? Like sometimes with bits of like basaltic like lava or magma, and then it's erupted at the surface. So we can see this rock here has like some basalt like on the outside of it, the darker stuff, and then peridotite's like the green stuff, and it's made up of olivine and pyroxene mainly. Right, that's your mantle. But basically, you get, you know, volcanic eruptions happening underwater here, usually forming like pillow lavas and stuff because it crystallizes very quickly. But if you had it forming, like for instance, a ridge setting, like for like that's tied in with maybe a geological hotspot like Iceland, then you would have it erupting at the surface. And I've got some examples here, like of Icelandic basaltic magma, right? Okay, so basically it's a partial melt of the mantle, and the reason it's like called mafic, which means it's like, it basically means that it's like rich in magnesium and rich in iron. So the minerals that make up basalt like are a combination like of pyroxene, olivines, plagioclase, like, and then you've got some amphibole sometimes in there as well. It's there's different magmas and stuff, right? So this basically, if we draw like a simple volcano, you know, like this will kind of like make its way through the crust. Sometimes it will crystallize in the crust, like, and form what's known as a gabbro. So if it crystallizes very slowly over geological time, a basaltic magma, because it's magma when it's in the ground, will turn into gabbro. This is an intrusive igneous rock. Anything that's into the crust, intrusions into the crust, is known as an intrusive igneous rock in geology. Anything that erupts at the surface is known as an extrusive igneous rock. So obviously this is buoyant. It wants to kind of like, you know, make its way up. Like it will kind of crystallize, and, you know, blobs of it will make its way up. It might like reach like and form a plug. Like it might form dikes, like, which are horizontal, like sorry, sills which are horizontal. Like, so this is a sill intrusion. Or it might form dikes which are vertical. And usually it will erupt at the surface as a fissure eruption. So what's been happening in Iceland recently, you've got the fissure eruptions, and eventually it concentrates into a cone, right? Like, and forms a cone. And when it erupts at the surface, because it's spewing out and, you know, crystallizing very, very quickly, it forms this fine-grained igneous rock known as basalt. And that's how you get basalt forming, which is madness, you know. Like, when it's in the ground, crystallizes very slowly over geological time, turns into gabbro. But when it erupts at the surface, it turns into basalt. Now, I've got a good few examples of basalt sitting in front of me that I'm going to talk about, because there's been several periods across like Scotland's geological history where we have had the crystallization of basalt. And the last one that happened was actually 60 odd million years ago, which was during the tertiary period, where we had the volcanism related to the opening of the North Atlantic Ocean, right? So as we've had this divergent plate boundary form between the two continents, because once upon a time we were attached to North America, and we were on a big supercontinent known as Pangaea, but Pangaea started to split apart, and also there was volcanism related to that, which we can see now in Iceland. But we can find that in like the west coast, on the west coast of Scotland, across some of the islands. We can find volcanic centres as well as magma and lava, like basaltic lava that's erupted during this period of time, during the tertiary period, right? So I've got some lava here, like, which is like from, not that one. It's very dark. It's actually got stuff running through it. It's got veins running through it, like, which is from the Isle of Skye. Like, and the Isle of Skye is a volcanic island. It's known for its volcanic rocks and that, right? And also its Jurassic rocks. But basically, oh my god, I'm going to smash my table. This is formed like due to the opening of the Atlantic Ocean, due to that divergent plate boundary. Now, it's not been the only time in Scotland where there's been volcanism, because when we look back during the Carboniferous period, we also had a rifting period within the Midland Valley. Like, during the Carboniferous period, the Midland Valley, where Glasgow and Edinburgh is just now, like, was splitting apart, and the crust was thinning. And when you get thinning of the crust, you get basaltic lava like forming and seeping up through the crust, like partially melting from the mantle. So that's moving its way up, and it's wanting to get to the surface, and then it erupts as lavas. And when we look at like places like the Campsies or like the Ochil Hills in Scotland near Stirling during the Carboniferous period, they're all basaltic in composition. They're basalt lavas, basaltic lavas that have spewed out. You also have like Edinburgh Castle that sits on top of like a plug, a volcanic plug, which is obviously used for defence and stuff, but that's basically intruded into the crust. Everything else around it's eroded away, like this. I've drawn it actually. And the same with Dumbarton Rock as well. They've both intruded into the crust, right? So for instance, you've maybe had like a volcano. You've had like the magma chamber down here that will crystallise into gabbro, right? That's partially melted from the mantle somewhere. It's made its way up, it's erupted at the surface, like as lavas. It's then crystallised in here as dolomite. You've got your sedimentary rocks and around it, because during the Carboniferous period you had a lot of sedimentary rocks deposited in this basin, because basically the plates were kind of moving and stretching the crust, allowing lava to come up, right? So what happens over time is the last ice age has obviously eroded all of this away. So you end up like, you know, like with this kind of stomp, like sticking out, and then they've built the castle on it, you know? That doesn't look like a castle, but you know what I mean. So there's a castle sitting on top of the volcanic plug. You've got like obviously the layers of sedimentary rock in around it, which are a lot softer. And the ice that sculpted Scotland's geology or landscape as we see it today is kind of just came in, like eroded all this stuff away first. And because that's harder and made up of dolomite, which is the in between gabbro and in between gabbro and basalt, is formed like this stomp that sticks out, and that's why they've built the castle on top of it. Same with Dumbarton Rock as well, that's exactly the same, like a volcanic plug. And because it's harder, the rock's harder, it's more dense, it's going to like withstand erosion and stuff. So that's that. And I've got some examples again of Carboniferous like lavas like that actually have like this feature in them known as amygdales and stuff. Like, but I'll move on to talk about like some of the features that you can find like in basalt. So when basalt erupts at the surface as a lava, you might find it has these like gas bubbles in it, these little wee holes in it, and they're known as vesicles, right? So the vesicles form because when magma like comes from like within the ground, like it contains all these volatiles such as gases and stuff. And when that erupts at the surface, those volatiles are released, meaning that the space that the volatiles were in, or the gas bubbles like were in, and that like basically are released into the air and form these little wee cavities that we can see in some of the rocks. So that's a vesicular basalt. Now sometimes we have what's known as an amygdaloidal basalt, and I always spell this wrong. But basically an amygdaloidal basalt is when you've had the same thing happen where there's been cavities forming in the rock, but what happens is the rock's buried at depth again after it's been erupted at the surface, so you've got other rocks like sitting on top of it. You've then had like hydrothermal fluids running through the rocks, like hot hydrothermal fluids that contain minerals, right? And they all precipitate out different minerals, like they form amygdales, which are usually plagioclase or quartz or calcite, and they can look like something like this, like they fill up the cavities like and form these amygdales. Like Sky's got some really nice amygdaloidal basalt. Like another type of texture that you can see in basalt is a porphyritic texture. And there's a few theories on how a porphyritic texture forms. I've actually got like one there, like I mean you can see some of the porphyritic texture there, but basically they think that some of the crystals, which are rectangular, usually plagioclase, crystallizes as the magma's moving through the crust, like because it crystallizes at a certain temperature. And when this crystallizes, it basically like allows the crystals to grow a little bit bigger, but then everything else, when it cools, like at the surface, when it erupts at the surface, like the ground mass, like in between these crystals, ends up crystallizing very quickly. So it's like a two-stage like cooling system, like that happens when you have this porphyritic texture form, which is madness. So basically that's your basics on basalt. I hope that makes sense. Yeah, we'll see. But rock of the week, basalt, woohoo! Okay, hiya. Look at where I am. I'm at Fingal's Cave on the Isle of Mull. Is that not class? Look at these basaltic columns. They're amazing. There's a wee boat going in right now. It's class. Right, okay, so I can't even remember what I was talking about, but we'll try again. So how do we get these? How do we get these beautiful basaltic columns that you can see here today? I'm going to tell you. So around 65 million years ago, 60 odd million years ago, there was a lot of volcanism on the west side of Scotland, right? That's what makes up some of these islands that you can see here today. The Isle of Mull as well has a volcanic centre on it. The Isle of Skye, Ardmurchan, like the Isle of Egg, like loads of little wee volcanic islands, right? And it was all due to the fact that we were splitting apart. We were at that mid-oceanic ridge where you had a divergent plate boundary form. Now a divergent plate boundary is where two plates move away from each other, right? And at the middle it's like, pushing away from each other, and it's subducting somewhere else where it's getting recycled, okay? So as this is happening, it's moving away from each other, you have all this volcanism, all this hot magma. There's a partial melting of the mantle, partial melting of the mantle, and it seeps up, and it's basaltic in composition, mafic, right? A basic magma that forms from the mantle. So as that seeps up through the crust, sometimes it gets stuck in the crust and forms magma chambers, other times it comes out the surface, like where we can see this today. So this is basaltic in composition. And these columns form like through cooling and contraction. It's like nature's little wee way of, shaping things. The way that they cool and contract against each other, they form these hexagons, sometimes squares, sometimes nine-sided things, which I can't remember the name of right now. What's a nine-sided shape called? Is it like a octagon? No, that's 8. Septagon 7. What's 9? Anyway, someone will probably comment. Ningagon. So they cool and contract in these hexagons that you can see here today, and it's absolutely mad. Now, because it comes out the ground quite hot, it's 1800 degrees Celsius sometimes, but it cools at 1200 degrees Celsius. So it cools very, very quickly like that it doesn't allow the crystals to grow. This is why this stuff's so fine-grained, so tiny, because these crystals don't have time to grow. But if this stuff was in the crust and sitting in the crust where it's hotter, the crystals have time to grow, and they will usually form a magma chamber, or a sill, which is horizontal, or a dike, which is vertical, right? Or a laccolith, or there's loads of different types of like intrusive igneous rocks. But this is an extrusive igneous rock. It comes out of the surface as lava and erupts as lava, right? And you get these columns that form. Now there's 3 different layers here. There's a bottom layer of basalt, there's a middle layer of basalt, and there's this top layer of basalt. Now obviously the middle layer of basalt we spoke about, the columns, they form perpendicular to this cooling surface. So obviously there's a cooling surface at the top and cooling surface at the bottom, so there must have been ash and stuff like kind of coming down around the same time as this eruption and stuff, and that's what's formed the top. And every now and then in the top as well you see some joints, but they're not like these. They're not like these basaltic columnar joints, so it's pretty cool. Anyway, I'm going to grab the phone and I'm going to show you guys, and hopefully there's no comments that say that that the sound's not working. Where did I see that rock bit that had like the crystals in it? Like, okay, so this is mafic. This is like the black basalt that forms. You can see it's tiny little beautiful wee crystals in the magma. See it? Yeah? My safe word, what? And then obviously you have the cave itself. Now my signal, I might lose my signal in here, but I'll try to show you guys as best as I can.